In this video, we'll look at an example problem very close to the one you have to do in homework 1. In this problem, we're going to look at how water potential can be used to change the shape of cells, the size of cells, and a big physiological response that occurs because of this change. So, in this example, it's shown that beans hold their leaves in a vertical position at night, and then change that. They move their cells into a horizontal position during the day so they can capture more sunlight. Pulvini cells are used to accomplish this. Pulvini cells are located right here at the location where that axis change can occur, and as they expand, the leaf is held in a more and more horizontal basis. So in order to get the leaf to this horizontal position, the Pulvini cells have to become bigger. In order to become bigger, they must obtain more water. Water will cause them to expand. The way to get more water into these cells is the import of solute, in this case sugar and potassium ions. When the sugar and potassium ions enter the cell, that draws water. Water goes down its concentration gradient into these cells. And that generates a physical pressure. That solution is pushing against the cell walls, and the cell walls are pushing back. There's your pressure. Okay, so how do we solve these problems? You've got to remember that in interstitial fluid, or in the cell, or anywhere else, water is has an osmotic potential, and it has a pressure potential. And if you can find out what both of those are, you know the water potential of that container. So let's make this the cell, okay? And it's also true that the interstitial fluid has a water potential, and that water potential is the sum of some osmotic potential and some pressure potential. Now, while you're getting used to doing these problems, and you're going to do lots of water potential problems in this class, turn the information you can get from a word problem into a table like this, and set it up so that water potential inside the cell and water potential in the interstitial fluid are right next to each other. So set up so the equation is water potential there and water potential there. And then you make that into a table. Okay, so this is a table, and I'm going to give each one of these components of water potential and water potential a column, and then I got to make two rows, because here's the cell when the leaf is in the vertical orientation, and here's the cell when it's in horizontal orientation. The question asks for the cell's osmotic potential when it's in the horizontal position. So this is the answer we're looking for in the end, the entry to this box. The cell imports solute, and as it does, the pressure in that cell goes up. So the pressure goes from 0.5 megapascals, I don't have to use units in my table, to 1.6 megapascals. Okay. What do we find out next as I read through? The Pulvini cells are at equilibrium with the interstitial fluid, both before and after moving. Okay, now, this has to be true. This has to be true because if a cell is neither expanding nor contracting, then it has the same water potential as its environment. If the water potential in the cell was lower than the environment, water would be coming in and it would be getting bigger. If the water potential was higher in the cell than in its environment, the interstitial fluid, then water would be leaving the cell and the cell would be getting smaller. So in both of these situations, when it's held vertically and when it's held horizontally, you know that the water potential inside the cell and in the interstitial fluid is equal. Okay, what other numbers do we have here? The interstitial fluid is not under pressure. Sounds like the interstitial fluid, in both cases, has a pressure potential of 0. It's not under pressure. Good. And has an unchanging osmotic potential of minus 2.4. So its water concentration must be plenty of solute in there, because it has a water concentration or osmotic potential of minus 2.4 megapascals, both before or both during the vertical positioning and the horizontal positioning of the cell. Okay, got these equations, know what we're looking for. Oh, you know, we've got more equations than you think, because I know already that osmotic potential plus pressure potential equals water potential, and here I've got that whole equation. I just need to solve this sum, and I see that it's minus 2.4. That's the water potential. Water potential in this case equals the osmotic potential because there's no pressure. Get the water potential of the interstitial fluid. But I still get two variables. Oh, but I have this equal sign too. This is at equilibrium with the cell. So that water potential is the same as the interstitial fluid water potential. And so I can fill in this box. The water potential in the cell is also minus 2.4 megapascals. And now I have an equation I can solve. And that's that minus 2.4 equals 1.6 plus whatever it is I'm looking for. Minus 2.4, that's the water potential, equals the pressure potential, 1.6, plus my mystery number, the number we're trying to find, the osmotic potential of the cell. So minus 2.4 equals minus 1 plus 1.6 plus what? Oh, this is going to be a negative number, much more negative than this one. I think that's